For computer vision object recognition, we're inherently interested in finding objects in images, okay? And that finding means essentially two parts, or they're sometimes combined. There's this notion of detection and labeling, right? So here on this picture of, person standing next to a car, I have to not only sort of say what's in it, I have to say, oh, okay, over here, and I'll draw a box, because a lot of these things are window-based, saying, okay, that's the car, and by the way, over here, that's the person. So in general, that's what you have to do, and the most common approach to doing that is referred to as windowing methods, all right? So there are lots of different ways of thinking about windows. We can start by thinking about sort of whole images, right? So here I have a picture of a couple of training examples of koalas and a couple of training examples of pandas. This slide, borrowed from Kristen Graham. Kristen has a thing for cuddly folks with big ears. So if any of you are cuddly with big ears, you can give Kristen a call. I hope Kristen's okay with that. So, clearly here I have my koalas. We've talked about koalas before, how they're not bears, right? That koalas are this thing. And here we have pandas, which are bears but are just mean. Anyway, and what we'd like to do is we'd like to somehow learn a way of discriminating between them and say, which ones are which. So one way of doing this would be to just build some sort of a holistic description of the entire picture with the assumption, we'll get to this part later, that the picture thing that I'm looking at is mostly the koala or mostly the panda. So what would be the simplest possible description? Well, here's one. How about I just build a histogram of the pixel colors? Now I'm showing it here as a single image, so it's black and white. You could do this in RGB and you'd essentially have 3 histograms. And you could imagine that basically you could try to determine that, these things look kind of pretty much different than this, so that might be a good descriptor to try to find where the boundary might be. You might try something even simpler. I don't know if it's simple. Yeah, I guess it's simpler. It's not a very good idea, all right? The same way we did in PCA, you can take all the little pixels, put them in a great big vector space, and you could say, okay, here are a whole bunch of koalas, here are a bunch of pandas, find me the boundary. Do you think that would work well, or do you think that would not work well? What do you think, Megan? You think it would work well?
No.
No. Okay. One of the problems is, if I shift the picture just a little bit, all those pixels move around in that feature vector. So a small change in the image is going to give me a large change in my feature vector, which is not something you want to have if you're going to have a good ability to discriminate between them. So that won't work. And what about the color thing? Well, you think if I just did that color and intensity thing, that would work pretty well?
No.
No! Okay, look, suppose I make it brighter today, or there's a shadow being cast upon the thing, etc., whatever. I get major variations in sort of the distribution of the intensities, okay? Do you remember when we were talking about trying to do tracking or trying to find things, motion? We were looking for what were called interest points. I hope you remember that, okay? And you remember interest points, Harris features, those kind of things, they were based on the idea of places where you had high gradients. Okay? In particular, those were where you had variations in the direction of the gradient as well. And the idea was that gradients' corners were quite robust with respect to changes in illumination. So if we take our koalas and our pandas, we can consider sort of edges, contours, the idea of these intensity gradients, right? Those things tend to sort of stay where they are in terms of, if I change the intensity. All right? But of course, we do have this problem that as I move the image just a little bit, I might get shifts in the location of where those pixels are. So now, you remember SIFT features? So we did the whole thing with SIFT features, which took histograms of the orientation, and we computed these little feature vectors, right? Well, here, imagine taking your picture and you just cut it up into, say, 4 quadrants, right? It's easier, right? So 1, 2, 3, 4. And I suppose I just compute some histograms of the orientations of the gradients in each of those regions. And I do that for each of these pictures, okay? It's robust with respect to illumination changes because the gradient's are there. Is it robust with respect to small shifts in the picture? Megan, yes or no?
Yes.
Yes, it is. So the reason that it's robust with respect to these small changes is that, if I move this guy's ear a little bit around, a bunch of pixels, the distribution of the gradients is in that quadrant is going to remain about the same. That's why down here it says locally orderless. What it means is that I'm not worried about exactly which pixel you're in. I've got a general distribution in one or two different areas of the image, okay?